Hi, welcome to our next lecture on Calculus 3. Today we are going to continue our conversation about applications of gradient. We are going to take a look at problems related to tangent planes and normal lines. So in this section you are going to see 6 basic problems. We have looked at some of them before, but this section has all of these topics all in the same place. We are going to look at these 6 questions in perhaps a couple of videos. The first question is find the equation of a tangent plane to a surface at a given point. So we have some surface, we want to find the tangent plane to it. Second standard question is finding the normal line to surface at a point. These type of problems should remind you of questions back in Calculus 1 where a curve was given and you were typically asked to find the tangent plane and tangent line and occasionally the normal line. Now we are in higher dimension and we are going to look at tangent planes and normal lines again. Then next, more advanced question is suppose we have two surfaces that are intersecting each other, they're cutting each other off, for example like this can or a cylinder, and then we have perhaps a paraboloid and perhaps this paraboloid has entered that cylinder. At the intersection of these two there's going to be a curve and we want to find out the tangent line to that curve. So that's a third type of a question that we're going to look at. Next question is inclination angle of a tangent plane to a surface. So suppose we have the tangent plane and we want to know what angle it makes with the horizontal plane. That would be similar to the question of finding what angle a tangent line makes to a curve. Next, very important question is what are the points on a surface where the tangent plane is horizontal? This has to remind you of the standard problem in Calculus 1 again, where you have a curve and you want to find the maximum or minimum of that curve. So the first step is to find where the tangent line is going to be horizontal, or the slope being 0. So we have a very similar scenario here. We have a surface in 3 dimension and we want to find the high and low points of it and so-called critical points of it, and that's what we are going to be aiming at. Next issue is more general issue of finding the angle between two surfaces. Let me remind you again, you had the same question, similar question in Calculus 1 where you had two curves and we wanted to find out what's the angle between the two curves. Now we are taking this one notch higher up. We have two surfaces again. Imagine these two blue and the black surfaces here, they're intersecting, and the question is what angle do they make between the two of them. Two particular cases are of interest when the angle is 0 and the angle is 90 degrees. When the angle is 0 we say the two surfaces are tangent to each other, and when the angle is 90 degrees we say the two surfaces are perpendicular to each other. So we are going to take a look at these questions. We have laid the groundwork for all of them in the previous section. We have actually solved a few problems related to this, but again let's take a look at them. It's a very important issue. Some of the main applications of Calculus 3 come up in the context of these type of problems. Okay, what's a groundwork? If you have a function of 3 variables like w is equal to f of x, y, z, if you set this thing equal to a constant, in particular 0, what you get is a level surface. So it becomes a level surface of that function. Now if you have a point in space, if you want to know if that point is sitting on that surface or not, if you plug it in that equation, if it becomes 0 then you know you are on that surface. Next important thing is that at that point on the surface, what is the normal vector? Normal vector, we said last time, it's a gradient vector evaluated at that point. So if you are at some point here on the surface. You want to find out what vector is going to be perpendicular to it. Simple. We take the partial derivatives of f with respect to x, y, z, evaluate it at this given point, and the vector we get is a vector that is perpendicular to our surface. Okay, let's make this thing concrete by looking at an example, see how it actually works out. Here's a question. Consider a surface given by x squared plus 2z squared equal to y squared. Suppose we want to find out the tangent plane and the normal line. So here are two things to find. Let's see. Find two things. Tangent plane and of course also normal line. Well, you have to specify at what point you want these things, because different points give you different answers. Here at 1, 3, minus 2. So this is my x0, y0, z0. If you take 1, 3, minus 2 and plug it here, of course 1 squared, 2 times 2 squared is in fact equal to 3 squared. So that point sits on the surface that is represented by this. How are we going to work it out? To make everything standardized, we clean things up by bringing everything to one side. So I have my function defined as f is equal to, now I took a y squared here, it becomes x squared minus y squared plus 2z squared. Now if this quantity becomes 0, I must be sitting on that surface. When this is 0 and this is 0, I am right on that surface that the problem is talking about. Next issue is, well, how do we answer these questions? Before we go there, let me just show you a little bit picture so that we kind of have an idea of what we are aiming for. So let's go here. I prepared something for you here on this nice and amazingly free website. You can actually go ahead and graph all sorts of things. We have looked at several examples of this thing before, but here let's take a look at it again. That equation I had there, x squared minus y squared plus 2z squared equal to 0, that gives us this cone. Let me erase other things so that things don't get crowded. Okay, so this is a cone. It's a elliptical cone, meaning it's not like the standard cones you see on the highways and such, because yeah, it looks like squished cone or something, but anyway, it's a cone. Okay, then we want to look at two things. One, a tangent plane to it, and second one is a normal line to it. So we are going to look at the tangent plane. So tangent plane, well, whatever you see here is a tangent plane. This plane barely touches that surface, and we call it the tangent plane. The question is, how do you find that? Next thing we want to find out is a normal line. So normal line here, you see this line that just emerged here. This thing is perpendicular to that surface, and of course also perpendicular to the tangent plane at that particular point where all three of them meet. So if you look at here, you can play with it. That's what we are after. We want to find these two. These are basic building blocks of calculus for approximations, for all sorts of calculations. We need, at the minimum, we need these two things. How are we tangent to something? How are we perpendicular to something? And of course, once we have that, then all sorts of other things can be done. Let's go back and see what did we say about the properties of the gradient. So the gradient is the main tool that brings everything together. What is gradient? It's really notion of a slope you had back in even high school. You had the rise over run, and then you came to calculus, and then you had derivative that gives you the slope. Now we have a whole slew of variables all over the place, and instead of one derivative you have to find a whole bunch of derivatives. We call them partial derivatives. Partial derivatives, you maintain a bunch of variables constant, you just change one thing at a time. So for example, here we have f. If I take partial with respect to x, so this was our shorthand for this partial of f with respect to x. By the way, this notation doesn't have a standard reading depending on which text you look at. Different people read it differently, so the long form of it is partial of f with respect to x, and let's just call it that. Sometimes they call it del f to del x, sometimes they refer to it as f sub x, and so on. So from the context and your instructor, you have to be clear as to what is meant. Well, the process itself was a lot simpler than the naming. You're taking derivative of this thing while holding y and z as constant. So obviously that is just 2x. Same story with respect to y. This is a particularly simple problem. So 2y, and then partial with respect to z is of course now 4z. Okay, so remember, we bring everything to standardize this deal. We bring everything to one side, so x, y, z, everybody is one side. The other side gets cleared out, so it becomes a 0. So that's f equal to 0, means you have a formula equal to 0, and whatever set of numbers satisfy that is going to end up sitting on a surface, and you want to analyze that surface. So in our case, y squared is equal to that would have been a elliptic paraboloid in direction of y, and now we are looking at this. Now we are looking at a particular point to point, or tangent plane changes, or normal line changes, and so on. So at let me write this thing higher up. At p0, so let's call this thing p0. Of course, you choose a particular value of x0, y0, z0. So it's going to be 2x0 minus 2y0 and 4z0. In our case, in this case, it becomes 2x0, that's 2. 2y0 becomes minus 6. 4z0 becomes minus 8. Is that right? That's z0 here is given in a negative number is given to us. So this is 2 minus 6, 8. So we can abbreviate all of this thing by saying the gradient of f. This gradient of f is this vector at this point 2 minus 6 minus 8. What is the claim to fame of this gradient? Well, really it is the big player here. It is the direction of the vector that's perpendicular to our surface. That's what we said, it's a perpendicular to our surface. And okay, how do we make use of it? Here, remember from basic geometry, if I have a vector here, let's call it the gradient of f is this vector. If you want to make it simpler to yourself, maybe call it normal vector n. What does it mean? It's normal to some plane or to some surface. What does that mean? It means it is perpendicular to any line you draw here. Regardless of what line you draw, this thing is perpendicular to that. Okay, first objective. How do I get the equation of this? In our context, we call that the tangent plane. So this is a plane. In our case, this is tangent to that our surface. Here is a very simple description that works with any dimensions and a very clean-cut formula, which is the following. So here you have a point. We call that, let's write it in another color. So x0, y0, z0 is some point at which you want this to be perpendicular to your surface or tangent to the surface. Then you have some plane here. Let's look at some particular point on that plane. Let's call that point X, Y, and Z. So this is my point P0. This is some arbitrary plane on that point on that plane. Let's call it P. So if I draw a vector from P0 to P, how is that going to sit with respect to N? Well, they are obviously perpendicular to each other. So here, if I have a vector going from P0 to P, that's a vector here, this red vector, or let me change the color. Let's call it blue vector here. So P0P is some vector. It is perpendicular to N. So if it is perpendicular, the condition was that the dot product was 0. Okay, believe it or not, that is the main step of just about every problem in this section, that these two things are perpendicular to each other. The only thing that's left to recognize what are the ingredients in each piece. So P0P is the distance from here to here. Well, how do you write the distance? Well, you subtract them. That's what your distance is. So let's say x minus, so I have a vector x minus x0, comma, second piece, y minus y0, third piece, z minus z0. So I have a vector in 3 dimensions as 3 components, which are these things. This blue vector is our displacement vector that is perpendicular to this normal vector. Well, who is normal vector? Normal vector is our gradient. How do we write our gradient? So let's write it. We are going to write it fx, fy, fz. Let's emphasize that all of these things are supposed to be evaluated at P0, not any arbitrary location, but that location that you're interested at. We are here. Okay, this dot product has to be 0. Well, when everything's said and done, what is left out of it? How do you do dot product? First with first, second with second, third with third, and add them up. So I'll have x minus x0 times f sub x evaluated at P0, y minus y0 times f sub y, again emphasize, evaluated at P0, plus z minus z0 times f sub z, one more time, evaluated at the point of interest. This has to be equal to 0. What is this? Well, x, y, z are the points that are sitting on that plane, and in our case this is going to become our tangent plane. So holy grail number 1, equation of tangent plane. So let's go back and see what happened again. Some equation is given, x and y, z in it, so that's a surface. To standardize, throw everything to one side, equal to 0. Okay, so that's a standardizing step. We bring everything to one side. Take the partial derivatives. So we have, here's a simple problem. Sometimes it's a bit lengthy, and then you take the partials. Then you are interested at a certain point. These are your slopes at the arbitrary point. Go ahead and evaluate it at that particular point, so you get a bunch of numbers. By now you have a vector of 3 ingredients. Then equation of the plane is x minus x of the given point times the partial with respect to x at that point, plus similar things for a, y, and z equal to 0. That's it. So the problem conceptually is quite advanced, but the procedure at the end is a one-liner. So what is the equation of plane in our case? Let's write it. X, our deal was that you go ahead and first and do this thing. So you go ahead and find out what's the equation of the plane. So you pause this thing, find the equation of plane, then you come back and compare. Okay, so that was our deal. Do your best, no cheating. You do your best to finish it up and then come back and to compare, and that way you know what you missed and what you didn't miss. Okay, so x minus x0, here's our x0 minus 1, fx, 99% of the time you want that number, not 2x but 2, because you want it at that particular plane, not all over the place. If you want to all over the place, then you have to write 2x0, otherwise this x and that x are different x's. Let me make sure you understand that. This is a x sitting on the plane, this tangent plane. That x is x of a point on the surface. These are two different things. Okay, so make it short. This is times 2 y minus y given point. Y given point was 3. Let me write these things in a parentheses so we don't make a mistake. Times minus 6, and then z minus z0. z0 was minus 2. So if something is minus, you put it in parentheses, not to make a mistake. F sub z was minus 8. So here this parenthesis also prevents us from thinking that we are subtracting. We are not subtracting, we are multiplying with a negative. Okay, now we are there, 99% we are there. Just to clean it up, tradition is to write these type of numbers up front. So you write it like first clean up, you write it like this. Okay, so that is one style you write your equation in. Another one is to clean it up one more level, so it becomes 2x minus 2 minus 6y plus what's that, 18 minus 8z minus, what's that one, 16 equal to 0. And well, here these three constants turned out to be 0. I have now 2x minus 6y minus 8z equal to 0. You can clean up one more level if you wish. Okay, so that is the equation of tangent plane. That's what we find, equation of tangent plane. So the process is pretty straightforward, but of course lots of advanced ingredients are built into it. So that is what how we find, let's see, so this green surface, this is the tangent plane. We found the equation of it. We had some different constants here than in that problem, but that's all the same. So like here you can make animations so that you can actually move things around. So I made this thing so that it stays tangent to that cone, and as you go around you show these two for a variable point of interest. What does that mean? So in this type of demos, the point of interest, you can change it, and in this type of software that is referred to as a slider. You're sliding around, so instead of being tied down to a specific point, you go after a slider that moves around and gives a bit of a feeling of animation. Okay, the next what was the next question we had here? We said we are going to answer two questions. Equation of tangent plane, so we are done with that. We did the equation of tangent plane. Equation of normal line to a surface. How are we going to do that? That's just as simple. Equation of line. Let me just refresh your memory from essentially algebra from high school. that how did we write the equation of a line? So if you want to go in a certain direction, so you have a line, you have a starting point on that line, and you're going in a certain direction. So that direction is specified by a direction vector. So for example, if you want to give somebody an address, you tell them go in this direction, or go in northeast or southwest or something. So you give a sense of a direction to a person, and the person of course is at a certain location. So you have a starting place. So starting place, let's call that the starting place P0, point 0. And then the line is a set of all points, let's call them P. You collect all of these points and I call it point P. Okay, if you have a direction to go, that means the vector from P0 to P, this vector that you're supposed to travel, is a certain multiple of this direction vector. Okay, so you have a direction vector that tells you which direction to walk on. So we said, for example, northeast or whatever it is, that you translate it to a vector. Then you have to take so many steps. We show it by parameter t. So if we take my direction vector, whatever it is, and multiply it by some parameter t, that's going to bring me to my destination. Okay, that looks so different from the formulas you have seen in high school for equation of a line, but that's really a clean-cut version of those equations that you had back in high school. They probably give you like about half a dozen different forms of equation of a line, like point slope, point slope, intercept, intercept, and so on. There are all sorts of forms of it, but really the common ingredient to all of these things is the property of a line which has a fixed slope. So how does it work for our case? We have at starting point, so you're in 3 dimensions, you're x0, y0, z0, so you're somewhere in space. You want to go some other place in space and stay on a line, so this one is x, y, z. First of all, what does it mean to go from P0 to P? Your displacement is a difference of these two. So your displacement is x minus x0, y minus y0, z minus z0. That is your displacement. Well, that displacement is supposed to be a multiple of your direction vector. That multiple, we call it t. Parameter t, your direction vector. Well, what's going to be your direction vector? In our case, our direction vector, we want to stay perpendicular to the surface. So our direction vector is the gradient again. So this one becomes fx, fy, and fz. Okay. And now these are this is a vector, that's a vector. The two of them are equal if the first is equal to first, second is equal to second, third is equal to the third. Let's write them down. So x minus x0 becomes a multiple of fx. Again, these are evaluated at that starting point p0. Y minus y0, that is t times f sub y. And z minus z0, that's also t times f sub z. You notice everything so clean cut and similar to each other. That is referred to as the parametric equation, sometimes written like this: x is equal to, take the x0 to the right hand side, same thing, tfx, y is y0, tfy, z is equal to z0 plus tfz. So this is the parametric form. Because t is the parameter in our equation. Sometimes uh, they ask you to write it close to what you had in a prior course, either calculus 2 or even pre-calculus. So sometimes your homework or web assign insists on something called symmetric form. It's simple rearrangement of this. The rearrangement is to extract t from all these cases and say, well, it's the same parameter t and these have to be all the same. So if we go back to this form, x minus x0, assuming fx is not 0, if I divide this by fx, if I divide by fx, I get t. Well, if I do the same thing, I get t, and if I do the same thing here, I get t, and these are all same t's, so they have to be all the same. So that's y minus y0, f sub y, and that is equal to z minus z0, f sub z. This is legitimate so long as you're not dividing by 0, of course. If any of these things is 0, then it means that variable and c0 are always equal to each other, and there's no change in them. So this is called symmetric form. So many of the problems ask you, for some reason they prefer this, but so anyway, so this is symmetric form. So there's another holy grail of us. What is the symmetric form of what? Let's write symmetric form of normal line to a surface, of course. So let's go back again and see what happened. Some equations given. Bring everything to one side to standardize it. Call it f. Take the partials. Evaluate the partials at the given point. So now you have 3 numbers. That's all. Then you're done 99%. Is x minus x of given point over the partial at that point. So for our problem, let's go back. Let's write it. What is, we wrote it up there, but let's do it again. What is the normal line to, what was it, x squared plus 2z squared minus y squared at 1, 3 minus 2. So step 1, f was x squared plus, excuse me, this was 2z squared equal to x squared minus y squared plus 2z squared. So gradient of f, which was fx, fy, fz, turned out to be 2 minus 6 minus 8. We did up the previous page. And then x minus x of a given point over the y minus the y of a given point. Now that's 3. Over the derivative, that's really slope in that direction, is equal to z minus that, z minus minus 2 is z plus 2 divided by partial in that direction is minus 8. Who is this? This is equation of normal line to the surface. That's the surface. So again, what we got, this, the equation of a line in higher dimension is made out of a bunch of equations. The number of equations that you have, or the number of equalities, is always one less than the number of dimensions that you have. In calculus 1, you just have x and y, and there's only one of these things. Calculus 3, x, y, z, you have really 2 of them. So what we found here, what we have is the equation of what you see here, this colored line, rainbow color here. That's the equation of the normal line. That's what we found, that normal is perpendicular to the surface and the plane, all of them touching at this point. Okay, so that's the main point. That is the clue to all the steps that we are doing to keep the videos short. Let's do a couple of these things at a time. So we did these two, and then we are going to come back and do another two and another two. Okay, good luck and God bless until the next short video.